So you have the right basic idea to take a derivative of L with respect to the grid F. So this is a 2y, good, minus a times the first of x. And then with respect to y, you have 2x minus a times the first of y. Then again, since this is a first order condition, we will set the derivative equal to 0. All right, so we can use the first order condition to solve for a. A is equal to 2y divided by the first of x. That's from this condition right here. And then a from the second condition is equal to 2y equal to 2x divided by the first of y. So let's equate the two expressions for a. 2y divided by the first of x is equal to 2x divided by the first of y. So let's cancel out the 2's, then rearrange, and we have that the first of y times y not t, is equal to the first of x times x. And then, finally, let's use the Dutch constraint. This condition right here. Hello, your son. Can you hear me all right?
Yeah, hello, sir. Sorry, I'm a bit late. I just
No,
go.
no problem.
Right.
So, M minus spending on X is equal to spending on Y. So we can substitute for this condition right here, the one from the budget constraint. So this is M minus spending on X. Let's gather terms on the left-hand side. And then there is our demand function for x. X is equal to m divided by 2 times the first of x. But I think your son got this all right. And people, mainly, you had the right idea, but I think maybe there was a typo somewhere in your result. It's equal to m divided by 2, not divided by 4 in this case. So, by symmetry, the demand for y is equal to income divided by 2 times the first of y. Is there anything strange about those results that may occur to you? So you remember that last Wednesday they had solved the Lagrangian of x times y, and then of the multiplier times the vector constraint. Like that. And for that utility function, xy, we found that the demand for s is equal to n com divided by 2 times the price of x, and similarly for y. So, in other words, we had exactly the same Marshallian demand functions for x and y in the original problem as we do in the new problem, even though we have different utility functions.
Yeah, when I was doing it, I thought that there should be some kind of a um, like because when I got exactly the same answers, I was like, it shouldn't be that easy. It should have been a bit harder than that. So I was unsure about my answer.
No, your answer was exactly correct. And yes, there was a trick involved with these utility functions that will simplify our life enormously. And the trick is, I'll bring it here, any positive transformation of a given utility function will yield the same Marshallian demand functions. We'll come back to the Marshallian in a minute. As does the original utility function. In this case, our original function was that u equals xy. And then the new utility function was 2 times xy. So the new function, I'll call this u1. Is a positive transformation of the original because it is twice as much as the original function. Therefore, according to the law, we will arrive at the same functions for x and y. The reason for this involves a bit of calculus. Do you remember the chain rule in calculus? If I could spell. Suppose that we have one function f that is a function of another function g. Then the derivative of f with respect to x is df relative to dg times the derivative dg relative to x. So here's an example. Suppose that g is equal to xy. And then f is equal to 2g. Therefore, the change in f, let me use small letter g here to be consistent. The change in f relative to x, using a chain rule, is 2 times dg dx, which is y. F is a positive transformation of g because df dg is 2, which is positive. So there is a chain rule. Why does that matter? Okay, well, let's look again at a general utility function, f, which is a function of g, and g is a function of x. Okay, so suppose that f is a transformed or a new utility function. And g is the original utility function. And then finally, x is a choice variable. In other words, we will choose x in order to maximize utility as expressed by f. So as always, we will take the derivative of the utility function with respect to x, and then set that equal to 0. By the chain rule, we have this product of derivatives and then by the first order condition, this is equal to 0 since we have maximized f with respect to x. Okay, so df dt is just a number. So that doesn't matter. Let df to dt be equal to 2, which is positive. So now we simplify our derivative with respect to x using the chain rule that's equal to 2 times dt over dx equal to 0. Divide through both sides by 2, and we have that dg dx is equal to 0 in this case. In other words, we may choose x to maximize g, the original utility function. And then by this chain rule, that same choice of x will maximize f. So the truth is, if f is a positive function of g, then the same choice of f that maximizes g will also maximize f. So if we don't like the utility function of 2xy, we can use something simpler and substitute it for the original utility function. We have the same solution to either of these utility functions. That's the idea. Okay, so let's put that idea to work. But looking at a question that your John had raised a couple of weeks ago. About problem number 2. The utility function is x to the power 1/3 times y to the power 2/3. So what that function over here, problem number 2. L to the Lagrangian is equal to x to the power to the power 1/3 times y to the power 2/3, and then the usual multiplier budget constraint. Okay, now one possible method of attack may be to maximize the Lagrangian by operating on x directly. So we have something like, this is 1/3 times x to the power of minus 2/3. Times y to the power 2/3, and then the budget constraint. And that's a possibility, but it is a real mess. It is messy because the original utility function is complicated. That is x to the power of 1/3 times y to the power of 2/3. Nobody wants to try to solve that regardless. So a simple method is to use a raw function of the original utility function. So the original function is x to the power 1/3 times y to the power 2/3. And that's it. So suppose that you take the natural log of u. So then we have 1/3 times the natural log of x plus, what's next? 2/3 of times the log, that's the log of y. Now we can replace the original messy non-linear utility function with a simple linear function through the log transformation. Because the log is a partial transformation of u, we will have the same solution to x and y. So call the natural log of u for v, doesn't matter. And the derivative of the v with respect to x is very simple. It's equal to 1/3 divided by x. Since you remember that the change in the natural log of x with respect to x is equal to 1/x. So what I recommend is that in problem number 2 on the extra credit, that you use the log transformation. I think it would be easier for you to follow. Okay, let's return now to a discussion of demand functions from last time. Okay, so far, can you still hear me? Good. So now we are going to take a look at income and substitution effects for demand. and then see whether they're useful when analyzing such policies as whether to subsidize the price of bread. So let's begin with a reminder of how the price effect may bear upon indifference curves. Here is you, a consumer of rice and meat. She is maximizing her bundle by choosing the tangent point for the indifference curve and the budget constraint. So you know that drill. And now we want to determine how a fall in the price of rice may affect her consumption. So what should we do in this graph? To show the decrease in the price of rice. Though since the price of meat has not changed, this point remains the same as before, the same vertical intercept. And then we have the TR is falling. So the horizontal intercept is moving out to the right. One way to think about this is that the horizontal intercept is equal to y divided by a lower number than before. So there is the solution. The budget constraint scribbles out, and then we maximize the useful method by finding the new tendency point. Okay, so far. So in this case, the new low price of rice induces you to buy more rice, and interestingly enough, also more meat. So we will come back to the reason for that in a second. Now here is another problem again for you. She is buying rice and meat. And now,
Chris, do you mind if I quit the lesson and because I have to go to a hospital?
oh, the meetings are optional.
Oh,
So
okay,
it's up to you.
okay. I'll be on tomorrow's lesson because I have to go to a hospital really quickly.
Oh, okay,
I'll rewatch the recording.
Okay, done. Yeah, good luck with you at the hospital.
Okay, thank you very much.
Okay.
Bye-bye.
So now the price of rice increases by 50%, and the price of meat rises by 50% as well. And then finally, her income goes up by 20%. How would this affect her demand for rice and meat? There is our original solution: meat in the quantity and store rice in the quantity of or star. Now, this happens if both prices and income go up by 50%. What is your guess about how that inflation may affect the graph? Well, um, let's go back to the whiteboard to see what the surprising solution may be. So here is the original vector constraint. The vertical intercept is income m divided by the price of meat. And the horizontal intercept is m divided by the price of what the rice. And now we have a 50% increase in income and also in the price of rice. So now our horizontal intercept is 1.2 times m divided by 1.2 times the price of rice, or and divided by the original price of rice. Exactly the same intercept as before. So what about the vertical intercept? How does this change in response to the 20% increase in prices and income? In versus the 20% and the price of meat also rises by 20%. In other words, you get the same intercept as originally. So, um, neither intercept changes in response to the inflation, and therefore the solution, this indifference curve, is also the same. So, the moral of the story is that sure, inflation does not affect consumer decisions. In principle, according to macroeconomics, inflation does not matter. Not sure inflation, which may be news to the macroeconomists. why not? Why is it the case that a proportional increase in both prices and income does not affect the decision of how much to consume? Though in general, a change in prices or a change in income can affect consumption by influencing the budget constraint. So, for example, suppose we have only a 20% increase in income, but the prices remain the same. Then, in that case, our budget constraint is shifting out. Looks like this. There are horizontal intercept is 1.2 times M divided by the price of rice, which has not changed. And the same thing for the vertical intercept. Both intercepts shift out, but the slope does not change. Why not? The slope is the ratio of the two prices. In particular, it is the price of rice divided by the price of meat. Since neither price has changed, the slope has not changed either. So in this case, the income effect does change consumption because it enables us to buy more meat and more rice than before. But if we have the same 20% increase in the price of rice and in the price of meat, then real income does not change in this story. Because the prices are rising as rapidly as income, the true inflation. So, one point for the macro economist is this. It is not pure inflation that we necessarily need to worry about, but instead the impact of inflation on relative prices. So if, for example, the price of oil rises more rapidly than the price of, labor, shall we say, then that will affect the decision of the oil refinery of how much labor to use to produce gasoline. So, in short, Can you see that? Okay. So we are going to assume from now on that, right now, uh, that we have a change in prices, but nothing in money income. The change in prices has two components. One is the substitution effect. And what is that all about? Suppose that the price of rice goes down more rapidly than the price of meat. Then rice becomes cheap relative to meat. So we will substitute rice for meat. That's the substitution effect. And here is an example. Here is the original budget constraint. And then there is a fall in the price of rice that reduces in magnitude the slope of the budget constraint. The overall, the fall in the price of rice will move us from the red point to the blue point here. However, for right now, we are interested in just one component of the price impact. We are interested in substitution of rice for meat when we hold real income constant. Utility is a measure of real income. So in the graph, the substitution effect brings us from the red point to the green point. So you can see that the green budget constraint is reflecting the new price of rice. The slope has become less steep, but we have situated the new budget constraint in such a way that we hold constant utility because we are on the same old indifference curve. So there is the substitution effect. We consume R2 rice more than the original amount of R star. The substitution effect is R2 minus R star. Okay, so far. The other component of the price impact is the income effect. And how can we show that in the graph? Well, let's see. Notice that the green budget constraint has the same slope as the blue budget constraint. So that means that we have held constant the prices at the new level. That is, the slope is now in magnitude the new price of rice relative to the price of meat that has not changed. So in moving from the green budget constraint to the blue one, we have an increase in income, holding prices at the new level constant. So the income effect is that we increase our consumption of rice from R2 to R1.
Only rice, not the meat?
Now the, uh, for right now, let's concentrate on rice. And then we'll take a look at meat. That's a good question. So the overall price effect on rice is the sum of the substitution effect and the income effect. The overall price effect is R star up to R1. Okay, now we can talk about meat. And take a look now uh, at the substitution and income effects for meat. All right, what is the substitution effect for meat? Now, again, the price of rice has fallen, which means that in relative terms, the price of meat has risen. The substitution effect is that we cut back on meat from M star up to R2, from here down to here. No surprise, we should expect that a negative that the increase in the relative price will reduce the amount of meat that we buy because we are substituting rice for meat. But in addition to that, we have an income effect for meat as well. The income effect is positive. With our money income, we can buy more meat and more rice than before, but we are shifting from here over to here. So the income effect is that we increase our consumption of meat from R2 up to N1. From here over to here. Like that. That is, the income effect for meat is larger than the price effect. So overall, we wind up buying more meat, even though it is relatively more expensive to rice than before. Something of an anomaly. And there is an explanation of the income effect. The intuition is that usually when our income increases, we want to buy more of most goods. Since our demand changes when income rises for most goods. So for example, if our income rises, we may prefer steak to hamburgers. And the income effect is to demand more state than before. Here is a numerical example if this will help. Suppose that usually we buy 10 cups of tea per week for 100 kg. So overall, you and I are spending 1,000 kg on tea. Now, the price of tea falls to 50 kg. The result is that we save 500 kg when we buy a usual 10 cups of tea. What are we going to do with our saved 500 kg? Well, probably we will spend those savings on a variety of goods, including tea itself. So we buy 11 cups of tea and not just 10. The income effect is one additional cup of tea. Okay, so far. Okay, so let's conclude with a paradox involving potatoes. So in this case, the price of potatoes has gone down. As a consequence, we have a rise in income in real terms, since we can buy more potatoes and meat than before. The income effect occurs from the red point to the green point. So what is happening to the potatoes? Is our consumption of potatoes rising or falling?
Falling in this case?
So, yeah. Is it a puzzling of the income effect, which is held constant, then the prices is actually negative? We cut back from T star to P1. Touchy-moo. Why? Potatoes, in our example, is what economists call an inferior good. Very simple concept. People want less of that good when their income rises. In the graph, potatoes are an inferior good since we cut back on potatoes just because of the rise in income. So, for example, people may purchase less beer when income rises because beer is inferior to champagne. Or for potatoes, a possibility is that people will buy steaks rather than potatoes as they become rich.
I'm sorry, does that happen because the price of meat also go down?
Oh, no, that's a good question. The substitution effect is always in the opposite direction of the price change. If the price of meat goes up relative to the price of potatoes, then people will buy less meat and more potatoes. So there is the substitution effect from the red point up to the green point here. The price of rice has gone down, and therefore the relative price of meat has risen. The substitution effect says that people always buy less of the expensive good than before. And that's what's happening here. We decrease our consumption of meat from M star that R2 goes down. That effect is always the same because we are moving on a negative slope in difference curve. However, the income effect may be either positive or negative, depending on whether the good is normal or inferior. So here it is for potatoes and meat. The income effect involves this shift in the budget constraint. Given prices, we consume more meat from about right here. I've not indicated it. The M1. So meat is a normal good. When our income rises, we buy more meat. But potatoes are an inferior good, even in a literal sense, I think. When our income rises, we buy less sugar potatoes than before. From here over to here, from T5 to T1. Or approximately T5, just about right there. Usually, most goods are normal, so that usually when our income rises, people buy more of most goods. But in this case, potatoes are an exception. If our sugar potatoes have become richer. Okay, so I will stop there. If you would like, to next time, you can use this puzzle to earn an additional 10 points of extra credit. This is then the PowerPoint slides for income and substitution effects. I'm going over time, so I will stop there.
Okay, Professor.
Questions?
Will we have all the lectures on YouTube? I mean, the records of that.
Yes, I can do that. That's fine.
Okay, that will be great.
Okay. So the bridge is dusty down there.
Okay,
Good night.
see you. See you.
Bye now.